Okay, folks, if you watched the last video, you heard that I'm teaching a class called Spacecraft Design this semester, and one of the chapters that I teach is called Attitude, Determination, and Control, and it's all about how the spacecraft knows where it is and where it wants to go and control itself there. And there's this problem here that talks about a drum-shaped Earth-orbiting spacecraft with a radius of 1 meter. It's spin stabilized with a certain amount of inertia, and then it's got a certain amount of inertia on the z-axis, and it's got 50 Newton thrusters mounted on the rim of the spacecraft. There are thrusters that are in pulse mode, and it's got a pulse width of 40 milliseconds followed by 60 milliseconds. How many thruster pulses are required to completely rotate the spacecraft around? Now, there is a crude analytic way to do this, which assumes a lot. And the assumptions are that here the change in momentum is originally upwards at 2000, and you want to change it to downwards at 2000, and then that means that you basically have to do a 4000 Newton meter second change in delta H. And if you assume that dH dt, right, if you go back to your equation, dH dt is equal to the total torque, and you ignore this term here, then torque times dt is equal to dH. So if you kind of think about it, if we know what the torque is, R cross F, and assume that's dH dt and bring the dt to the other side, we get this equation, and then we have to make some assumptions about the pulse signal, and we have a square wave, and we kind of did some math in here and there, and we ended up getting 29 pulses. Well, it turns out that this math was actually wrong, so we did it again, and I got 2,000 pulses. Now, this problem has been a source of heated discussion in the classroom, and I kind of want to completely remove all of the assumptions, or not all of them, but as many as I can, and actually simulate this spacecraft and for once and for all determine how many pulses does it take to spin the spacecraft completely 180 degrees around, okay? So I've got my Python ready to go here, and I'm going to copy some stuff. I just need, let's see, I need this guy to integrate. I'm going to call this spin stabilized satellite.py. Let's see, I need my derivatives routine, derivatives, and then let's see, my derivatives routine. Actually, I can just copy this and then delete that. Oops. Okay, so that's going to be that guy, and then to simulate down here, I need state initial conditions and things like that, and we'll worry about what my initial conditions are later. Okay, so what are the equations of motion? Well, dH dt is equal to T, the torque applied, times minus omega cross I omega. Okay, so we need in inertia matrix, which is as array, I need the first row, which is IXX 0, 0. I'm assuming it is a symmetric spacecraft, and then 0, 0, IZZ. Now, they only give us IZZ. They tell us that the spacecraft has an IZZ of 500. Now, I'm assuming that if the spacecraft is long and slender, 500, I would assume that the X and Y ones are bigger because it's probably a cylinder, and so I'm going to say that IXX is 500, or sorry, 800, and then IYY is IXX, and then call that a day. So there's my inertia. Then I need my angular velocity. Well, I'm actually going to make that my state vector. So I'm going to make unpack my state vector, and I'm going to say omega x is, and I'm actually just going to make this W of 0, and then omega y is W of 1. Actually, I don't actually know if I need to do this, because it's a 3 by 1 vector. Okay, so there's my inertia, so I just need my inertia matrix. I also need the torque on the spacecraft. Now this is where things get hard because I need to model pulse jet thrusters. Oh crap! So that means I need to code my own RK4. So I'm actually not going to use scipy.integrate or this. T-out is fine, but I need to grab. Let's see. Do I have like an ODE int ODE? LMNO. No, there's no O. Here's controls. I bet you here's an ODE int one. Yeah, do I have like an RK4 coded up? Let's do a search. So let's go documents, file, GitHub, Python. Let's do a search for RK4. How about Runga? Okay. We're just gonna have to go for gold here. Okay, so let's code this in. So here's the thing. We need to have a pulse off time and then a pulse. Well, here. Yeah, let's do pulse duration is 40 milliseconds, right? And then pulse wait duration is 60 milliseconds, okay? And then pulse off time is going to store the last time we shut the thrusters off. And then the pulse on time is when we turned the thrusters on, okay? So basically, I want to pulse all the time. Like I want to go as quickly as possible. So I just want them to be on all the time. So what I'm going to say is if t is greater than or equal to the pulse off time, so that's the last time I turned on the thruster, I turned off the thrusters, plus the pulse wait duration. And actually what I'm going to do is I'm going to make the last time we turned on the thrusters negative pulse wait duration. And the reason why is because I want them to fire right away. Okay? So if that's true, I'm going to say thrusters is equal to 1. Okay? I'm going to initialize thrusters equal to 0. Okay? And then if I turn the thrusters on, I spelled pulse wrong. I need to set pulse on time equal to t. Okay? So that is going to, I think I need an and here. So I think I need a, actually I don't want thrusters off to be in here. I want thrusters 0, and I want this to be a Boolean. So what I need to do is first check and see, are thrusters currently on? Okay, so if thrusters equals 1, thrusters are currently on. Okay, so then do we need to turn them off? Okay, so that's, if they're on, we need to check and see if we need to turn them off. So if t is greater than or equal to when I turned them on plus the pulse duration, right? Plus the pulse duration, then I need to turn thrusters off, okay? Then the next time I come through the loop here, thrusters are currently off. The question is, can I turn them back on, right? So, and that's where I do this. So if t is greater than the pulse off time, okay, so here I turn them off, and then I need to tell the computer when I turn them off, which is the pulse off time, okay, equals t. And then, can I turn them back on? I say, if t is greater than when I turn them off plus the pulse wait duration, then the pulse on time is t, and then that's it. And then down here, I can just say my torque is equal to my R crossed with my force, and R is just 1 meter, and F is 50 newtons. And I'm going to say time the thrusters. So if thrusters is 0, it's 0. If not, it's not. Okay? So there's my pulse jet thruster model. So now I have my torque, I have my inertia, which means dH dt is my torque minus, and then I can do NP cross omega, NP dot matmol, inertia, and omega. And that's dH dt. And then dW dt is I inverse NP linalg dot INV. This is ridiculous. Inertia inverse. This is a really easy equation because it's a diagonal matrix. So inertia inverse is just 1 divided by IXX, 1 divided by IYY, and 1 divided by IZZ. And so there's inertia inverse, and then I guess matmol, NP dot matmol of that times dH dt. And then I return dW dt. Okay, I think that's right. So to make this easier on ourselves, I'm going to make torque 0, just to make sure the simulation is doing what I think it's doing. I'm going to make the initial condition 0, 0, 0. Okay, I'm going to simulate for 450 seconds, sure. I have to do my own RK4, so I have to say 4, T, and T out. So I need to actually save 3 vectors. So I need to say W out is NP zeros, 3 comma, len T out. Okay, let me see if this runs. I forgot to put parentheses in the right spot. Okay, so if I do np dot shape of W out, I get a 3 by 10,000. Okay, so that means I can say 4T and T out. Okay, I can say dW dt is derivatives of, and I have to give it W and T, and so it's going to be W out of all rows, comma, ooh, I have to keep a capital counter, and so I'm going to say that, comma, counter, and then T, and then at the bottom here, say counter plus plus. Oh, plus equals 1, I'm sorry. So let's see if that runs, it doesn't throw any error. Thrusters referenced before assignment. Don't I have thrusters up here? Do I have to make thrusters a global? Oh, I already spelled thrusters wrong. So I guess I gotta do thrusters, pulse off time, pulse on time, and then these I can just hard code these. Pulse weight duration. Pulse weight duration. Oh. Shoot. Okay, I guess I'm making these globals. My brain is not, I'm tired. So I'm going to say, oops, pulse, weight, duration, and pulse duration. There we go. Okay, so it ran. Okay, so now what we need to do is do our RK4. So RK4, here we go. So you have dW dt1 is derivatives of W out, all comma counter, comma T, and then dW dt2 is derivatives of, here, let's do this. Let's say Wi is W out of and then I'll do wi, and then this is going to be wi plus, I need a time step. So dt is t out of 2 minus t out of 1. And so I need dw dt of 1 times dt over 2.0, and then t plus dt over 2.0. And then call it again, derivatives of wi plus dw dt2 times dt over 2.0, t plus dt over 2.0. And then dw dt4, the fourth function call, RK4 has 4 function calls, dw dt3 times dt, and this is a full time step, and then you do phi is 1.0 over 6.0 times dw dt1 plus 2 times dw dt2 plus 2 times dw dt3 plus dw dt4, and then w out of all comma counter plus 1 is equal to wi plus dt times phi. Now, because I'm doing counter plus 1, I need to go from 4t, so actually I kind of want to change this. So I want to say for counter in range 0 comma len of t out, and then unfortunately I'm going to have to do a wi, and I'm going to do a ti, is t out of counter, and then I don't need this counter plus equals 1 down here, and then I just change all my t's to ti, and that's a ti, and then that should run invalid syntax. I need a colon. Oh boy. Index is out of bounds. Oh, because I forgot to do len of t out minus 1. That's what I was trying to tell you. I just lost my train of thought. Okay, so that ran. So then we can do, so I mean dw dt1 should just be a bunch of zeros, by the way. Yeah, it is. It's up here. You can see it. It's just a bunch of zeros. So this is going to be pretty boring, but if we just do plt.plot dw dt with respect to time, that's it, right? plt.show. Okay. Oh, not dw dt, sorry, w out. So we should see 3 lines on top of each other. What's len of t out? And then len of w out? Whoa, what happened? What's wi? And then phi? And counter? Oh, I did len, np shape of w out, sorry. And then len of t out? Okay. So why can't you plot t out and w out? They must have the same first dimension? Okay, can I just do np transpose then? And then force it to have the same first dimension? Okay, that makes me feel better. Okay, so let's make this thing spin. So how do I make my initial conditions? W out of all comma 0 is np dot as array 0, 0, 0. Okay, and then let's make this thing spin by 10. And so it should just keep spinning. Okay, cool. Let's throw a grid on here. plt.grid, plt.x label, time in seconds, plt.y label, what do I want to call this? Angular velocity in radians per second. Okay. Alright, beautiful. And then let's make sure, let's do about the other axis. Okay, cool. Let's do multiple axes, and I think because the inertia matrix is diagonal, I think they should all just be constant. Cool. Okay, so now let's turn on our thrusters. So let's get rid of the 0 here, and let's allow the thrusters to kick on. Okay. Yeah, it looks like there's just some chattering here, which is pretty normal. There's our angular velocity, so that is working. Oh yeah, I made, I made torque. It's mp.asarray. It's in the, so if it's about the, it's spinning about the z-axis, so I guess I'm only applying torque about the y, so it's 0, comma, r times f, comma, 0. Oops. So there we go. Okay, that makes me feel better. So, yeah, there's only torque applied about one axis. So that's good. Okay, let's see. How do I get the number of pulses? So every time I turn the thrusters on, this is when I turn the thrusters on, number of pulses plus equals 1. And up here I'm going to do number of pulses equals 0. And then over here do number of pulses. And then I guess I'm going to print, I'm going to simulate for a second. I should only get 10 pulses. Print number of, should I only get 100 pulses? Because there's a duty cycle of 40 milliseconds with a wait time of 60, which is 100 milliseconds. And then 1 second is 1,000 milliseconds divided by 100 is 10. Local area. Number of pulses, number of pulses, number of pulses, number of pulses. I only got 1 pulse. I broke it. Okay, let's do this. So thrusters are supposed to be off. So print turning pulse, turning thrusters on. Oh shoot! Wait, no. I think we're okay. I was gonna say, like, normally with like controllers like this in an RK4 routine, like you should only call the controller once. I wonder if that's what it is. So maybe what we should do is make torque an input. That's probably what we should do. No, hang on, I don't want to close it, I just want to delete that. So I'm going to make a def thrusters. The input is just time. Okay, and then I can move all of these globals to here. Okay, and then this thing is going to take in T. Let's just see if this fixes it before I start putting print statements here. And I'm going to return the torque. Okay, and then here I'm actually going to make torque an input, and so torque is actually an input. And then down here I actually need to compute torque is equal to thrusters. Is it thrusters plural? Yeah. And then give it TI, and only run that once, and then give this torque and torque, and then torque. Should have just done T. Alright, let's see if that, oops. Missing one required argument. Derivatives. Down here? Wait, why do I have this? Why is this here? Number of pulses is 1. Oh, do I just have the math wrong? Is this 40 milliseconds? Yeah, 40 over 100, my bad. 40 over 100 with 0.4, I'm dumb. Yeah, you swoop it 3 times. No, you swoop it twice. No, mil was 1,000. So is it 1,000? 10? What did I have here? That was just to get the duty cycle. But 100 milliseconds is 0.1 seconds. 100 milliseconds is 0.1 seconds. Yeah, you divide by 1,000. So 40 milliseconds is 0.04. So this is what it is. So there's my 10 pulses. So pulse, wait, pulse, wait, pulse, wait, pulse, wait, pulse, wait. Okay. So we are in business. Okay. So if here's the kicker. If my initial angular velocity is, so I have 2,000 Newton meter seconds. So I can do this pretty quickly if I just do 2,000 divided by 500, right? 2,000 divided by 500. So that's spinning about the z, spin stabilized. I need to figure out how long it's going to take before the whole satellite is oriented the other way. Looks like it's like oscillating. It's like it doesn't even have enough thrust. It's so stable, I can't actually get it around. The book did say that there were 4 50 Newton thrusters. So maybe we just need to multiply by 4. How do you... Yeah, it's like it's just like oscillating. Maybe I should have, let's put in, oh man, this is gonna go crazy. Like roll, pitch, yaw, right? And then when I plot this, so if I do W out of 0 all, I get the first row. And if I do 0 to 1, if I do 0 to 3, if I do 0 to 4, yeah. So if I do 0 to 3, I get the first, second, and third row. So let me make roll, pitch, yaw the last variables. Oh no, but then I've got to change all this. Oh my goodness. What I want to know is see if like maybe it's doing this, but maybe it's rotating. Like if I plotted roll, pitch, and yaw, that's what I want to know. Because this is just showing me the angular velocity, and this is all in the body frame. So like I want to know what the vehicle is doing in the inertial frame, which means I need. So alright, this is just going to take a while. Sorry for the long video. So I'm going to have state 6. I'm going to do roll, pitch, yaw. And then I'm going to, this is all good still, except when I go to my derivatives routine, this is no longer W, this is state. And this is state. And then this is state I, and then I guess I'm going to copy this, and then paste, oops, paste, 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 and then state out, state out. Let's see, let's do dstate 1. I know it's dstate dt, but this is fine. dstate, dstate, dstate 4. There's state I. Okay, so this is dstate 1, dstate 2, dstate 3. That's torque is good. Phi. I don't want to call this phi anymore. I want to call this chi because I don't want to confuse it with the roll angle. So there's dstate 1, dstate 2, dstate 3, dstate 4. On. And then this is state out. And then this is state I, not IO, not an equal. And this is, no, that's chi. Okay, this still looks good. That's state out. Okay, and then, so this is what I was trying to do before. W out is state out of, it's 3 comma all, so, or it's 6 comma all now, so it's 0, 1, 2, 3, 2, 4, 5, 6, comma all. Hopefully that'll work. And then this will plot W out, and then roll pitch yaw out is state out of, and actually I just want to plot pitch, no, because the yaw angle is spinning like crazy. I want to plot like the roll and the pitch angle, so I want RP is state out of 0 to 2. Alright, so if I do W out of 0 to 2, of all the rows, do I just get the first 2 rows? Okay, cool. And then if I did 1 to 2, I'd get the second row, I think. Yeah, hopefully this is working. Okay, so then I'm going to plot this again, except this time I'm going to do RP, and then this is going to be roll, comma pitch, and this isn't in radians per second, it's in radians. Okay, now we have to go to the derivatives routine, and now the state matrix. So W is state of 0 to 2, 0, 1, 2. No, it's going to be 0 to 3. Because it always stops at the one before. And then roll pitch yaw is state of 3 to 6. I think I need to print RPY and then print W. And then I'm going to make this 1, 2, 3, 4, 5, 6. And just make sure that this is working right. Okay, cool. So RPY is 4, 5, 6, good. And then W is 1, 2, 3. Okay, cool, we got it. All right, so this is good. So I'm going to make 0, 0, and then again the 2000 divided by 500, and then 0, 0, 0. Okay. And then dw dt, this is still good, but now we need a drpy dt, and then we're going to return np dot, is it concat? No, it's hstat, or vstat, hstat. How do you use hstat? Let's see. A is np.asArray 1, 2, 3, and B is np.asArray of 4, 5, 6, np.hstat of A, comma B. Okay, cool. So I want to do hstat dw dt and then drpy dt. Okay, so then what I need though is I need, and I don't actually know if it's in this book, because I need the equations of motion of Euler angles. grab a different book. Or just grab different code. I feel like I've got code in here. Where's 6DOF? Here we go. 6DOF. So in here I'm pretty sure I've got, here's derivatives, here's phi theta psi, here's PTP, kinematics. This is it. So this is an H matrix. It's got like, oh, signs of, oof. Okay, so I just need all, I just need all of this. Okay, spin stabilized. Alright, so we're gonna tab all this over. And then, so we need phi is roll pitch yaw of 0, theta is roll pitch yaw of 1, psi is roll pitch yaw of 2, right? Roll pitch yaw. And then that makes all of that. I don't need this because I'm not simulating the position. And then rather than calling this the H and calling this the J matrix, and then I'm going to do matmul of J, and then not PQR, but W, which W is defined up here, and then that gives me DRPY dot. Okay, sweet. I think I've got it. If this works, blast. Of course not. DRPY dt, DRPY dt, DRPY dt. It's there. What are you talking about? Oh, I did dot. This is dt. Okay. Dude, I'm running out of steam here. Been screencasting for like an hour. You know, PLT.figure. PLT.figure. Okay, so let's see. So W out. So I did this backwards. W out is actually 0, 2, 0, 3. And then roll and pitch is 3 to 6, or 3 to 5. There we go. No, so roll and pitch is just, it's just, let's plot, can we plot yaw? Let's plot yaw. Yeah, so there's the yaw angle, which is blown up because it's spinning around the z-axis. But it's not actually spinning. It's just like, it's like so stable, it won't turn around. So let's just plot this again. I'm at 5,000 pulses and it hasn't moved. So roll and pitch is just constant. And there's roll rate and yaw rate. Okay, let me just make sure I'm not like losing my mind. Like if I throw a 0 here, right? Is it gonna spin around? Yeah. Yeah, I mean there's pitch. It just completely flips over. Like it doesn't even take that long. I mean, that was like 1,000 seconds. Like how long does it take to just go, 3.14 radians? Yeah, I mean, it takes like 8 seconds, like 100 pulses. Okay. Well, I'm going to pause the video. I guess I haven't answered the question, how many pulses does it take, because I can't get it to spin. It's just so stable. So I'm going to mess around for a little bit. I mean, the code works, in my opinion. It's so stable when you apply the pulses, it doesn't spin around. So I'll mess around with it for a little bit, and then I'll come back, and I guess I'll tell you what I found. Okay, folks, I couldn't figure it out. I don't know. I've never dealt with spin-stabilized spacecraft. I mean, I spun the thing down to like 1 radian per second. I mean, like, if you spin it down to, 0.2 radians per second about the z-axis, like, it does start to move a little bit more, but it's still spinning about that, alternate axis. And I mean, you look at the roll and the pitch angle, and I mean, it still does some weird stuff. I don't know, I guess I've never seen something like this. So what I did add though while I was gone was I added this variable called pulses is equal to t out, and then here I actually saved the thrusters variable in the pulses and then plotted it. And then it's kind of neat because you can actually see, you know, when the pulse jet thrusters like turn on and then turn off and then turn on again and then turn off, and so it, you know, kind of turns on and off in this duty cycle here, which is kind of neat in my opinion. So at least now you know how to code pulse jet thrusters if you wanted to do like a control system. But yeah, I don't know. I guess that, like I said, the satellite is so spin stabilized. If it's spinning and you flick it, like it just starts to wobble. You know what I mean? If you start giving it like significant, you know, angular momentum about that axis, and you hit it, I mean, it's just so stable. Yeah, exactly. So you just get like, you know, a little bit of deviation in the roll and the pitch axes. So I don't exactly know. You know, I was looking at this problem and I don't see it. You know. But I guess anyway, I guess at least the Python code's working, so maybe you can mess around with it and maybe you can figure it out. So I'm going to stop the video here. This is a long video, 40 minutes already. I hope you enjoyed it, and I guess I'll see you in the next one.